Hello everyone. This is Kaidun Zhang from University of Science and Technology of China. It's my pleasure to share our latest progress on video in painting. The title of our work is Flow Guided Transformer for Video in Painting. We have released the codes and pre-trained models on GitHub. Welcome to visit the project page by scanning the QR code. Video in painting requires a sequence of video frames and the corresponding frame-wise mask to indicate the regions we focus on. The aim of video in painting is to achieve spatiotemporal coherence across the in-painted video frames, and the alternation should be as imperceptible as possible. Its application includes watermark removal, object removal and video retargeting, etc. Currently, there are two types of strategies. Flow-guided methods restore the corrupted optical flows first, and guides the content propagation across all frames through the video, while transformer-based methods encode multiple frames and utilize self-attention strategy to fill the corrupted regions. Flow-based method FGVC maintains video details, but suffers from the flow warping error, which introduces disorganized structure artifact. Although transformer-based method Fusiformer is expert in synthesizing complete structure, it struggles to recover details in high fidelity. A method aggregates the benefits from flow-guided method and transformer method to maintain the complete structure and rich details simultaneously. Besides, we also noticed that the performance of transformer-based video in painting method can be boosted by the motion discrepancy exposed in the completed optical flows. Given the input frame and the corresponding mask, the result from the pure transformer shows the adhesion effect between the red car and the background. If we adopt the completed optical flows as guidance, the transformer can synthesize clear boundaries. Here is the main pipeline of our method. Our method contains two stages, including a flow completion network and a transformer model for frame synthesis. First, we introduce the local aggregation flow completion network, LAFC. In LAFC, we integrate the P3D blocks in the encoder to exploit the complementary features from corrupted flows in a local temporal window. Moreover, we design a novel edge loss to supervise the edge regions in the completed flows with a small edge extractor and canny operator. In quantitative analysis, our method achieved much better performance than previous flow completion baselines. What's more, the steady improvement introduced by local aggregation and edge loss also demonstrate the worth of our method. In the qualitative comparisons, we observe the synthesized flow tends to retain more complete structures with local aggregation and clear motion boundaries with edge loss. Here we introduce the flow-guided transformer. Since the optical flows are local correlated, we decouple the spatial and temporal processing of transformers and only integrate the completed flows to the spatial transformer. In such manner, we can fully utilize the guidance from optical flows while saving considerable computation cost. Here is the flow guidance integration module. We enrich the frame tokens with the flow tokens encoded from the completed flow map. In order to control the region adaptive impact from flow tokens, we design a novel Re8 flow module to modulate the frame token map with a region-aware mask predicted from the flow and frame token maps. The quantitative metric gets improved with the flow guidance integration and flow Re8 module. Moreover, it's obvious that the introduced Re8 flow module can correct the shape error in completed flows due to the imperfect flow completion. To save the computation cost, we design elaborated window partition strategies for FGT. In temporal transformer blocks, we utilize large window to compensate the token offset between different frames. In spatial transformer blocks, we integrate global tokens to local windows to achieve local coherence with considerable receptive field. With the introduction of local, global tokens and the integration of flow tokens, we observe steady improvement in both the subjective and objective metrics. Here is the quantitative analysis between our method and the video in painting baselines. We adopt PSNR, SSIM and LPIPS to measure the objective quality of different video in painting methods comprehensively. Our method achieves significant improvement against the counterpart S on both eTube VOS and Davis datasets in multiple types of masks. As for qualitative analysis, we compare our method with previous counterparts. Our method enjoys outstanding visual quality compared with previous methods. The videos synthesized by our method have both rich details and complete structure. We also provide video-wise comparisons. We also perform a user study to validate the subjective quality of our method. A majority of volunteers prefer our method against the other competitive video in painting baselines. In summary, our method can maintain the high-frequency details and complete structure simultaneously, and the adoption of completed flows can also guide the synthesis in the transformer for better video in painting quality. Finally, the elaborated window strategies also helps our method strike the balance between performance and efficiency. Thanks for watching. Welcome to visit our project page.